In classical physics, we often have traveling waves that look something like this. This, of course, describes a wave moving to the right. Such a wave function could describe the traveling electric field or displacement on a string, pressure in the air. And a wave equation that might correspond to this would be something like the following. Where these symbols represent the partial derivative. With respect to x. So leaving everything else constant, like time. It's easy to see that this particular sinusoid satisfies that wave equation. The first partial derivative of y with respect to x is just ka cosine x minus omega t. The second partial derivative we're receiving the first partial derivative with respect to time. Gives me omega minus omega a cosine omega t. So it does seem to be true, for example, that this particular sinusoid also satisfies the wave equation. Written like so. As long as v is omega over k. But this has an interesting feature to it. This only works for traveling waves moving to the right. In other words, some general function f of x minus vt. But if you wanted to describe a traveling wave moving to the left, this would be described by a general function f of x plus vt. And implies that we would need a wave equation with something like this. So this is why we resort to second derivatives, because the second derivative will always cancel out that minus sign right there. And so that the wave equation works for both left and right traveling waves. So we can try such a sinusoid for matter waves as well. Let's see if this would work. Here k is proportional to p. Actually what it is it's p over h bar. We know that second derivatives have to be involved. So we can describe both left and right traveling waves. So we can write down what is d psi squared dx squared. This would equal minus k squared a sine of kx minus omega t. If we're looking at the time derivative, we'll stop at one derivative here. Because one time derivative gives me minus omega a cosine kx minus omega t. We're stopping because we want a relationship something like h bar omega is h bar squared k squared over 2m for a free particle. So we wouldn't expect to have a second time derivative here.